And again, I'd like to welcome you to today's TechNet webcast, Windows Hang and Crash Dump Analysis. We're coming to you live from TechEd 2006 in Boston. Today's presenter is Mark Rusnovich. He's the Chief Software Architect at Winternal Software. And we're going to pause for just a moment while Mark takes the stage live in Boston. So please stand by.
Welcome not only the people in the room, but this is being live webcast. So how about everybody in the room welcome the people that are on the web listening in. I also want to thank, before we start, Vince Orgavan, who's the head of the Windows Online Crash Analysis team, and Silvio, who's on the team with him, who are serving as the subject matter experts for the web audience. They're answering questions live as a favor for me. I really appreciate them doing that. And I also, because this is webcast, I want to apologize for a little bit of the awkwardness that you're going to see, because this is a very demo-intensive talk, and unfortunately, live meeting won't install on 64-bit Windows. So I'm actually going to have to TS into my machine to show you the demos, and I'm going to have to switch back and forth between live meeting and the terminal server console. For those, how many people have seen me present already this week at TechEd? How many people haven't? Let's see that. Okay. Welcome to the new people, and welcome back to the people that have seen me before. Just briefly, a little bit about myself. I'm Chief Software Architect and co-founder of Winternal Software, a company that specializes in Windows infrastructure products, and co-author of Microsoft's official book on the internals of Windows called Windows Internals with David Solomon. Also, a lot of you probably know me from SysInternals. This is the outline of what we're going to cover today. I'm going to first talk about crash dumps and the tools that you need to use to analyze crashes. Then I'm going to talk about a few basic concepts that make the job of both understanding crashes and analyzing them easier, and those include IRQLs and stacks. Then we're going to jump right into looking at crash dumps, starting with a very easy to analyze crash dump, move on to unanalyzable crashes, which I'll explain the reasoning behind that term as we go along, show you some examples of transforming those unanalyzable crashes into ones that you can analyze, and then I'll conclude with manual analysis, where the automated analysis doesn't help you. How many people in here have analyzed a crash dump before? Okay, keep your hands up. How many people have done that successfully? Okay. Well, that's a pretty good number of people. So what are you doing here? Actually, what are you doing? What is anybody doing here? Windows doesn't crash anymore, does it? In fact, I only got this talk into TechEd because I called it how you used to troubleshoot those crashes that used to happen on older versions of Windows. And then I changed it the last second. It was too late for them to pull it. So many systems administrators, unfortunately, don't analyze crashes because they don't know that they could do it. They think it's too hard. They think even if they take all the time to learn how to do it, that it's not going to tell them anything anyway, so they don't even bother. What you're going to see here in the next 75 minutes or so is that basic crash dump analysis is actually really, really easy. It's so easy, it's just like point and click and you're done. Even if only a handful or some small percentage of the crashes you look at actually reveal an answer, and you'll understand why some crashes just won't reveal an answer, it's still worth taking a few minutes to analyze crashes. I want to do a level set here, though. I'm not going to make you crash dump analysis experts in 75 minutes. In fact, it would take weeks and weeks and months of eating, living, breathing crash dumps, like the critical problem resolution engineers at Microsoft PSS, who are dedicated, focused on analyzing Windows crashes. Those guys are so good that you can give them a dump of physical memory, and they'll be able to look at it, and by looking at the bytes, say, oh, there's a pool header right there, and there's an ERP right there, and following that, there's a file object, and figure out how to traverse stacks without the help of the debugger. That requires intense knowledge of x86, x64, and even Itanium assembly language for those guys. It requires understanding all sorts of different calling conventions that Microsoft applications and third-party drivers use to call each other so that they can analyze the stack. And it also means lots of experience working with Windows internals to understand what these objects are, how they connect together, and recognize their footprints when they're looking at memory dumps. So I'm not going to be able to take you there, but I'm going to take you far beyond, hopefully, what the basic sysadmin that might know that you can analyze crashes is able to do. I'm going to show you a couple of tricks that will transform those unanalyzable crashes, those ones that they aren't able to analyze, into ones that you get an answer out of. First, how many people have ever seen a crash out in the public someplace? Windows blue screen in some public place, right? It's probably, I'm guessing, airports, right, ATM machines. I've got to actually keep a collection of crashes, crash pictures, that reminders, that I'd like to share with you, starting with this one. This is a British Telecom telephone that's blue screen. This is an ATM machine at San Francisco International Airport. This one is kind of interesting because Dave and I teach a Windows internals class. We taught a public seminar in San Francisco, and right after the class, the last topic is crash analysis. The attendee goes to the airport and boom, presented with a crash. This one's at a Barcelona train station vending machine, ticket vending machine, and somebody's obviously gotten really upset with this blue screen, plastered red stickers all over the box. It's a little Christmas cheer over here at the airport, over on this monitor. And airports are, like I said, a frequent place where you see these things. Here's at a baggage claim. Here's at another baggage claim at Zurich International Airport, and this one shows Microsoft's dedication to their international customers. If you look at the text at the bottom of the screen, that useless message about contacting somebody else to help you, it's been translated in German so that they feel comfortable with that. This is CompuSA's bestseller, which I just don't get. And for those of you that have seen Dave Solomon and I speak together, he was here earlier this week co-presenting with me. This is him going on personal vacation at LaGuardia's Continental check-in counter, and he's got this smug expression on his face. His wife took this picture of him because he'd analyzed the reason for the crash and turned to the people behind him and is explaining it to them. Not that I think that they really cared. This is probably the largest blue screen ever. It's on one of the largest hotels in the world. Anybody recognize that? When I zoom out, you might. Las Vegas's MGM Grand Hotel. And if that's the largest, this is probably the most public. This is a famous intersection in New York City, Times Square. Brian Valentine, who's the head of Windows development, happened to be walking through the intersection on the day this appeared, which I think was some really bad timing on the part of seeing the blue screen. He obviously made him very upset. This is just a block away at the Times Square subway station. It's really annoying that they haven't tilted the screen so that I can fully read the text and figure out what happened. And this is Iraq's former information minister. He did such a good job over there that they've hired him. This is a shirt that's blue screen. Actually, you can go buy this shirt online at a company called errorware.com, ERRORWEAR.com. And I supplied them that image for the shirt, and in return, they gave me a complimentary copy of that T-shirt. And I just want to give you a word of advice. If you're ever on Microsoft's campus and you're wearing this shirt, stay away from Building 26, which is the NT Development Building. Especially stay away from Brian Valentine's office, especially if it's the first time you meet him. And I'll just leave it at that. And this is what most systems administrators end up doing after they can't figure out what the problem is. So with that, let's return to the slide deck. Here's a little gyration I have to go through. See if I can get this to work. There we go. So why does Windows crash? A lot of you probably have thought at one point or another, hey, why doesn't it have like a 3 strikes and you're outlaw? Well, the Windows only crashes when something in kernel mode goes wrong. User mode code cannot, because of the protection mechanisms built into the operating system, cause a problem that results in the operating system turning over and bellying up. So something's gone wrong in kernel mode for there to be a crash. Kernel mode is a trusted environment in the Windows operating system, just like it is in most operating systems. Any drivers and the operating system kernel code itself can access basically anything they want to. They can access data buffers that are sitting in the file system cache about to go out to the disk. They can access even user mode code if they want to and data. And when a component detects that something's wrong, it's got one primary responsibility, and that is the preservation of your data. Because what might have happened already is corruption of buffers that belong to SQL Server data store or your PowerPoint presentation file. And if the system were to say, hey, you know what, we're just going to ignore that one. Let's see if we run into another problem before we give up on this thing. that could result in kernel mode code going and overwriting that data that's about to go to disk. So it wants to stop corruption from happening, and if it's already started to happen, stop it from continuing. So the thing, its job, its way that it gets that to happen is just stopping right away. And it does that by presenting the blue screen to death. Some of the kinds of problems that cause the kernel to give up like that are unhandled exceptions, like executing an invalid instruction. A driver of the kernel detects that there's some big problem with its data structures. They don't look the way it expects them to look. A driver accessing memory at a high interrupt level, pageable memory at a high interrupt level, the famous Urkel not less or equal crash, another very common type of problem. Giving up a thread telling the scheduler that it wants to give up the CPU and have the scheduler pick another thread when the interrupt request level is too high is another violation of the internal rules of Windows, and that would cause a blue screen as well. And finally, hardware errors, of course. Windows, when it detects those kinds of problems, might crash as well. Microsoft has analyzed the kinds of crashes that come into their online crash analysis site and determined by looking at them what the root causes of those blue screens were. And this is data from about a year ago. Talked to Vince recently, and he indicates that the numbers are about the same today, maybe plus or minus a few percentage points in each category. That roughly 70% of Windows crashes caused by third-party driver code. 15% they can't figure it out because the crashes are so bad that there's no information there. Roughly 10% caused by hardware issues that include memory problems and disk problems. And roughly 5%, they admit, caused by Microsoft code. I think that's big of them to come out and say, hey, yeah, we're still responsible for some part of this. But they're getting a lot better. The problem that Windows faces, and the reason Windows has for a long time had this reputation of being a buggy operating system, it isn't really the fault of Windows. It's the fault of Windows success. And Windows success means that lots of people are making devices for Windows. That means that lots of people are writing drivers for Windows. Lots of people that probably shouldn't be writing drivers for Windows. If you look at these numbers, they're pretty staggering. And these, again, are about a year old. The numbers are just accelerating as Windows just continues to grow and grow and grow. Over 55,000 unique drivers, 24 brand new drivers, never seen before, released every day. And if you include revised drivers, the numbers are even more impressive. So let's talk about what happens now at the time of a crash. When something in kernel mode detects a problem, it shuts down the machine by calling a function called debug. And that function takes 5 arguments. The first is called the stop code, and that's the component's high-level reason for why it's decided to crash the machine. The other 4 parameters you have to interpret with respect to what the stop code is. For a particular stop code, the first parameter might mean something. For a different stop code, might mean something else. debug turns off interrupts, tells all the other CPUs to stop processing, paints the blue screen to death. Drivers can request notification of the crash, and they might want to do this if they want to shut down their hardware in a safe way. And now if a dump is configured to do so, it takes a dump. It writes a dump to the disk. Now the stop codes are also called bug check codes, and there's about 150 defined stop codes. But throughout your usage of Windows, you're only likely to ever see the same handful. The 2 by far most common stop codes, or really 3, are Urkel not less or equal, which is usually caused by an access of an invalid memory location, or paged memory that's been paged out when the IRQL is too high. And the other 2 kind of go hand in hand. Invalid kernel mode trap and K-mode exception not handled. Those are usually generated by executing garbage instructions, or when the stack of the thread executing a kernel mode becomes corrupted and it tries to return off into La La Land. Most of these stop codes are actually documented in the debugging tools help file, and you can also search Microsoft's knowledge base for information about them. But most of the time, the stop codes and those parameters are not going to be able to help you really figure out the cause of the crash. In fact, because of the way Windows is configured by default, you might have systems in your organization that are crashing on a regular basis that you don't know about, because Windows automatically reboots after it has a crash. And unless your end users happen to be there during that crash, they come back to their office after lunch or in the morning, and they think, hey, maybe a patch was applied, or maybe some group policy setting had to take place, and I was logged off the machine, and now I've got to log back in again. When in actuality, the system crashed. So one thing I recommend you do is go back and audit your event logs to look for systems that are crashing. I think some of you might be surprised. So in order to analyze a crash, you need to get the system to generate what's called the crash dump, which is a copy of some or all of physical memory. And Windows has a few different crash dump options. I'm going to switch over to the laptop to show you that dialog box. And you get to this configuration dialog box through the system applet, which I like to get through by right-clicking on my computer, going to Properties, and then going to Advanced, and going to Startup and Recovery Settings. And here at the bottom is the system failure area where you configure these things like write an event to the system event log, send an administrative alert, automatically restart the machine. Down here at the bottom, you configure what kind of crash dump you want. And I'm going to pull this down so we can see the options. You can see there's 4 of them, and they range all the way from none to complete memory dump. Let's start with the complete memory dump. Complete memory dump was the only option available in NT4, and that causes the machine to write a full copy of physical memory to the crash dump file you specify. Its advantages are that there's no more information available to you. That is the full state of the system at the time of the crash, so it's not like you're leaving stuff out. That's the most that there is. The disadvantage of the complete memory dump is that it can be monstrously huge, right? Now you have systems regularly with 2, 3 gigabytes of memory, and that's a gigantic crash dump file. You also now have commonly servers with more than 4 gigabytes of memory. On 32-bit systems, the largest paging file you can have is 4 gigs, so you can't even generate a complete memory dump on those systems. On the other extreme, you've got the small memory dump, which comes by a couple of other names. One is the triage dump, and another one is the mini dump. On a 32-bit Windows XP system, or Server 2003 system, the mini dump is 64K in size. I'm running 64-bit Windows here, XP, so it's 128K in size. On Windows Vista, it actually can vary in size, because more information can be written into there. The benefits of this, the pros of the mini dump, are that it's so small you can actually really easily send it as an email attachment off to somebody. The con, though, is that it's so small that there's not much information there. And unless the cause of the crash is obvious in that data that was saved, you're not going to be able to figure out what happened. So kernel memory dump there, right in the middle, I think is a really nice compromise. Kernel memory dump is just a copy of physical memory that is owned by the operating system and the drivers, the system parts that are mapped into the system address space. You're excluding the user mode code and data. And as I explained, user mode cannot cause a problem in kernel mode. So if you're looking at analyzing the crash, all of the information you need is in kernel mode memory, including all of the data structures that are useful for analyzing the crash, like the list of processes that are active and the drivers that are loaded on the machine. How big is a kernel memory dump? Well, it depends. It depends on the way that your system is using kernel memory. And on my 2 gigabyte laptop, when I generate a test dump, a kernel memory dump, I get somewhere in the neighborhood of 256 megabytes in size, and this is a 2 gigabyte laptop, like I said. But your mileage is going to vary. So what I recommend you do is configure all your systems for kernel memory dump. Now, the defaults on Home and Professional XP is small memory dump, and the default on Server, if possible, is complete memory dump. So this is a change that you're going to have to go out and make. On Vista, they've changed it to default to kernel memory dump. Another advantage, by the way, that I failed to mention of the mini dump is that you get a copy of each dump file with a unique name in the mini dump directory under the Windows directory by default. So if you've got more than one crash on the same day, each one gets the name mini, date, month, year, dash, and index number. And it will keep those forever until you go and delete them. So you get a full history of the crashes the system's had. But that doesn't mean that you're losing that benefit with the kernel memory dump, because it turns out, because of online crash analysis, which I'll talk about, that any time an XP or Server 2003 system crashes, at the reboot, no matter what you've got configured, either kernel or complete dump, the system will extract the mini dump out in preparation for you sending it off to Microsoft. So you get the mini dump for free when you configure a kernel dump. And these next few slides just talk about this. Let's talk about what happens when the system crashes now, and you've got it configured to write a crash dump. In that configuration dialog box, you might have noticed that you can configure the target dump file for the complete or kernel memory dump. And you know that the mini dumps go to that directory. But crash dumps are not actually written to those target locations, those target files at the time of the crash. They go to the paging file. Not just any paging file, but the paging file on the boot volume. And if you know Microsoft's terminology, you know that boot and system volumes are two of the terms with the most ridiculous meanings ever defined in the history of computers. And that's saying quite a lot, I think you'll agree with me. Because I don't think you can get any worse than take those terms, think about what they should mean, and then just switch them. And the boot volume then means the volume with the Windows directory, and the system volume, the volume that boot.ini and your other boot files are located on. So it has to be the paging file on the Windows volume. But how is that even protected? The reason that it writes to the file instead of just the target is that to write to a plain old file, it would require the help of the file system driver, the IO manager, storage drivers, and it simply can't rely on those things being stable at the time of a crash. So it checksums components involved with writing a crash dump at the time of a boot. At the time of the crash, it checksums those components again, makes sure that they're intact, and then writes directly to the paging file's sectors on disk, bypassing file system drivers and using a small subset of functionality that's provided by disk drivers. The reason that the crash goes to the Windows directory or the Windows volume is that that's the only volume on a Windows system that you can't make a striped volume or a volume set. So means that there's a one-to-one correspondence between a sector on the volume and a sector on disk. There's no mapping that has to take place between those two other than an offset. And so it can safely know, hey, if I know the paging file is in these sectors, occupying these sectors on disk, I can write directly to those sectors. Further, the paging file is one of the only files now that you can't defrag while the system's online. So once it gets its map of where it is, it knows that that's where it's going to stay through the life of that system's current boot. There are cases when you configure this system to generate a crash dump where you actually don't even get one still. For example, because the crash goes to the paging file, paging has to be turned on for the crash dump to get written. The paging file is not initialized until a certain point into the boot process. So if the crash happens early in the boot process, for example, when a boot start driver is initializing and it causes a problem, the system can't write to the paging file. Also, if the crash has corrupted components involved with writing the crash dump, you're not going to get a crash dump. A spontaneous reboot is another type of crash, but it's not so elegant as getting the nice blue screen of death. How many people have seen your system just spontaneously, boom, reboot? And that happens when you have a triple fault on an x86 processor. This processor gives up. It's actually two unhandled exceptions. The processor gives up and says, hey, the operating system's out to lunch. I'm just going to go ahead and reset because there's no point in continuing to fault like this. Another reason is the paging file is too small, and you run the risk of that when you configure your system for kernel memory dump because, like I said, the system can't know ahead of time how big a kernel memory dump is going to be. So if you do configure your systems for kernel memory dump, set a paging file that's large enough to occupy, hold all of physical memory, generate a test dump under kind of normal workload and see how big that kernel dump is, and then you can shrink the paging file if you want to. Finally, not enough free space to extract the dump, or the system hangs. And I'll be talking about how to troubleshoot these kinds of problems, crashes that don't have dumps, a little bit later. At the time of the reboot, the session manager process, one of the first user mode process on the system, initializes paging, determines that there's a crash dump in the paging file, and then marks that area of the paging file as off limits for use. A little bit later, WinLogon, the Windows Interactive Logon Manager, starts up. It looks to see if there's a crash in the paging file, and if there is, spins off a process called SaveDump, whose sole job in life is to read those data from the crash data from the paging file and write it out to the target location you've specified. I'll take questions at the end. If you've crashed Windows XP or Server 2003 system, you know that when you reboot, you get presented a nice dialog that apologizes and tells you that, or asks you to send in the crash information to Microsoft to make Windows better. What's happening is that your crash is being sent to a place called Online Crash Analysis. And you can configure this with group policies or computer properties, an advanced tab, error reporting dialog. This slide also talks a little bit about how you can configure the crash reporting options. But what gets sent to Oka when you actually do send a crash is an XML file that has a description of your system, what version of Windows you're running on, what drivers are configured on your system, as well as a mini-dump file. Hence, you get the mini-dump for free. That mini-dump gets sent up to a server farm. And at that server farm, behind it, is a warehouse in Tacoma where there's a bunch of Windows developers that failed the security audits from 2 years ago, kernel mode developers. If they have a security problem, they're sent for a 1-month stint at some point to the Oka warehouse where they've got to analyze crashes. And if you think that's bad, and that's why if you work at Microsoft and an office mate disappears for a while, that's where they've gone. They can't tell you. And what's worse, if they've been caught with 2 kernel mode security problems and they get another strike against them, they get sent to the warehouse and they've got to analyze the crashes with Notepad, which is extremely difficult. I'm just kidding, of course. There's actually an automated server farm that does the exact same kind of analysis you're going to do, that I'm going to show you how to do. That server farm, that automated analysis that Oka performs, has both an advantage over you and a disadvantage over you doing it. The advantage is, during its analysis, it comes up with a unique signature for the crash called a bucket ID. And it looks in the Oka database, looks it up, that bucket ID, and if there's an entry in the database for that ID, that means that some human has analyzed this type of crash, has figured out what the problem is, and figured out what the resolution could be for you. Like there's a new version of a driver or a hotfix, and you get taken to a page that helps you out. The disadvantage that Oka has is if it does that lookup and there's no entry in the database, then it can't tell you anything. Underneath the hood, the analysis engine almost always comes up with some suspicion. And behind the scenes, Oka is going, I bet it's that video driver right there. I know that guy did it. And then it looks in the database, and there's no entry for this crash, and it goes, oh, you know what? I'm sorry, but here, let me take you and show you what it looks like. It says, oh, I'm sorry, a device driver has caused a crash. Have a nice day. And I've told you that the reason that you get crashes is something gone wrong in kernel mode, and most crashes are caused by a device driver. So not terribly helpful. The problem that Oka's faced with is that they've got this strong suspicion that this particular driver's caused a problem, but if they threw it up in front of you, guess whose lawyers would be calling who else's lawyers within minutes to complain about their smearing of their good name in front of their customer. So Oka's forced to only tell you about things that some humans actually looked at. Now, no disrespect to Vince or the Oka team, but when XP was released, this Oka thing was new. And I started experiencing these crashes on my system whenever I opened a help authoring tool, opened one of the help files I was working on, and went to a certain page in that help file. Bam. Almost always I'd get a crash. I was reluctant to send my data into Microsoft because back then there were privacy concerns over Microsoft spying on what you were doing. I guess those concerns are still there today. But at one point I was just like, you know what, I'll go ahead and send it in and see what's going on. So I send in the crash, and I get taken to this, which tells me, hey, we know who caused the problem. Here's the fix. Sure enough, I'd had an out-of-date driver. I went to that Windows update or that NVIDIA site, downloaded the latest version of the driver, and the problem was gone. I never experienced it again. That was the first time I used Oka. That was also the first time that Oka was successful for me, and unfortunately, it was the last time. So it got me all psyched up, and then now I'm back to manual analysis. So let's talk about some basic concepts now, starting with how you analyze a crash yourself. And you're going to need a tool to analyze that crash. You get your choice here. The package is called the Debugging Tools for Windows package, and you can just go to Microsoft's site, search for Debugging Tools for Windows, and you'll be taken to the Debugging Tools for Windows homepage, which has a bunch of information about using it, as well as the download links for both 32-bit and 64-bit systems. Within the debugging tools, there are 2 tools that you can use to analyze crashes. Which one you use depends on whether you like GUIs or not. And I know that there's lots of people still out there that like command prompt interfaces, including kernel developers in Microsoft, who wear their usage of the command prompt as kind of a badge of coolness and serious technical prowess. So if you're one of those people, you're going to want to use KD. If you're more like me that likes having multiple windows and you can switch between and see lots of stuff at the same time, you're going to want to use WinDebug, and that's what I'm going to be using throughout this session. The first thing you've got to do when you download and install this debugging tools is give it a pointer to the symbol files for the version of the OS that you're going to be wanting to analyze a crash from. So I'm going to go over to back to the laptop here and fire up the debugger. And the place where you configure the symbols is in the File menu under the symbol file path. Back in the old days, to do crash analysis, you had to go out and get the symbol files from the DVD or CD that Windows came with Windows, or go to the Windows website and download it from there. And then you had to do your own file management of keeping track of which versions of the symbol files you had, which version of Windows they were from, and pointing the debugging engine at the right one for whatever crash you're looking at. Microsoft's made this brainless now with something called the symbol server. And I've configured the debugger here to use the symbol server. The magic syntax there is that SRV prefix. And then within the stars or the asterisks, you specify the directory under which you want it to manage symbols for you. And then you point it at the symbol server website. No need to write this down, actually, because it's right on the debugging tools homepage in the help file. What this causes is that whenever the debugger looks at a crash, and it needs the symbols for a particular image that it sees, like the operating system kernel, it looks in that local cache directory that you specified, and if it can't find it, goes to the symbol server and pulls it down and sticks it there. Let's go take a look at what that directory looks like on my machine. So I put it under C symbols, my favorite place to put it. And you can see that there's directories there for a lot of different Windows components. I'm going to search for mtkernelmp.pdb, and you can see that for the multiprocessor version of the operating system kernel, I've analyzed dumps from three different crashes with 3 different versions of that operating system file. And they're identified with a unique hash number so that they don't collide. And if you look in one of those directories, you'll find the actual symbol file, the PDB file for that particular version that the debugging engine is going to use. Our next concept is IRQLs, and you've all been exposed to that term when you've seen the IRQL balance or equal bug checks. IRQL stands for interrupt request level. In the Windows operating system, each processor has its own notion of an interrupt request level that it uses to mask off interrupts. So it maps hardware interrupts and software interrupts into its own internal IRQL table, and when an interrupt comes in from a particular device, for example, it raises the IRQL of that processor up to that level that it's defined for that device, and that causes interrupts from other devices at that level and below, including software interrupts, from being masked off until this interrupt has finished being serviced. The key IRQLs on that chart are passive level at the bottom, which is what Windows tries to remain at all the time. Even when it's in kernel mode, it wants to be at passive level, meaning that no interrupts are masked off. User mode code is always executed at passive level, so you can never be in user mode code at any higher IRQL. Kernel mode code can raise the IRQL up, well, of course, in response to a hardware interrupt, but also for certain software operations, like synchronizing between 2 CPUs in the operating system kernel. That's done by acquiring something called a spin lock. And when a spin lock is acquired, the IRQL is raised up to that second level right there, dispatch level. Dispatch level is a level that causes the scheduler to get turned off, because the Windows scheduler relies on internal synchronization at that level. And this causes 2 rules to come into effect for device driver developers. One rule is that their thread can't yield the CPU. If they're at dispatch level, they can't tell the scheduler, hey, I need to wait for something to happen, go find another thread to run. The scheduler is going to go, hey, I can't do that right now. You're violating my synchronization rules, and it will call KE bug check EX with IRQL not less or equal. The second rule that they've introduced is introduced at this level is that page faults cannot be serviced. Page faults, because what happens for a piece of memory, if a driver tries to access a piece of memory and that memory's physically present, well, there's no page fault, so, which is fine. But if that piece of memory happens to be, virtual memory happens to correspond to data that's out on disk, like in the paging file, or an image file, or data file, then a page fault is going to occur. And the memory manager tries to service that transparently. It's going to issue a disk I/O to go read that data that has just been faulted for. Now, what does that thread do while that I/O is in progress? It has to wait. And waiting is a violation of that first rule. So the two rules are somewhat interrelated, but those occur at dispatch level. The next concept is the stack. And the stack is an area of temporary storage. Each thread in Windows has two of these, one that it uses while it's in user mode, one that it uses while it's in kernel mode. The user mode stack is usually 1 megabyte in size. It's up to app developer to control that. That's the default. And the kernel mode stack is usually 12 kilobytes. Some threads in kernel mode have larger stacks if they're doing Windows stuff of 20 kilobytes. But you can see very small stacks in kernel mode. And what stacks allow is for nested function execution, where a developer divides their code up into different subroutines. And when one function calls another function, something called a stack frame is created. You can see over here on the right side that a parameter has been passed to this function over here by placing that parameter on the stack, in that stack function stack frame. Then the system jumped to that function, but it recorded the address that it came from so that after that function's done, it can get back there. This function has used that temporary storage both to set up a frame pointer and to store local variables that are temporary and will be released off the stack, deallocated from the stack when that function returns. That function calls another function, you get another stack frame. And this function 1 calling function 2, it's passing 3 parameters. The return address back into function 1 is saved here on the stack, and then function 2 has set up its own frame pointer and local variables. And that can continue indefinitely. Stacks are very easy to interpret if the functions use what are called standard calling conventions, where they set up an explicit stack frame as you saw on that slide. But there's calling conventions that are used by the Windows drivers and the operating system that don't do that. They don't do it for performance reasons. So there's no frame pointer or frame pointer emitted calling conventions, and then there's passing arguments in registers instead of on the stack. A debugger, in order to interpret stacks that have those non-standard frames in it, requires the symbol information for the function that owns that stack frame. And that's always going to be the case if you're looking at Windows' own code, the operating system kernel or other Microsoft components. But third-party drivers don't typically make their symbol files available. It's part of their IP. And so the debugger can run into situations where it has to make guesses. And you're going to see, as we analyze some dumps, where it spits out a message that says, hey, I don't know really what the stack frames look like here because I don't have information for this particular driver, but I'm going to take a guess. Most of the time, its guess is right. But if you're troubleshooting a serious problem and you have a relationship with the vendor of the driver that you think might be causing the problem, get them to share the symbol file with you so that you can better analyze their dumps. So let's turn now to actually generating a crash. And what I'm going to do first is generate what I call an easy crash. The tool that we're going to use is a tool that I wrote. It's available there in that zip file on sysinternals, both in executable and source form. Believe it or not, I'm willing to share this super advanced crashing technology with you guys. And the tool that you're going to run is called Not My Fault. That name actually accomplishes 2 purposes for me. One, if you run it and crash your machine, it's not my fault. It's your fault. But the second purpose that it accomplishes is that it highlights the fact that using user mode code, you can't directly crash the system. You have to rely on something in kernel mode. And Not My Fault has a buddy in kernel mode called My Fault. That driver does the actual crashing. Just Not My Fault tells it how to crash the machine. So let's generate an easy crash. And before I do that, let's talk about what Not My Fault is going to cause My Fault to do. My Fault is going to allocate a block of paged kernel memory. Then it's going to free that block of memory. Then it's going to raise the RQL up to above dispatch level. Then it's going to touch that buffer, not only that buffer, but continue going through memory as far as it can go until it gets stopped by something. The reason why it's doing all of these really bad things, it's touching, first of all, memory that it doesn't own anymore, memory that belongs to other drivers, and touching paged memory at an RQL so high, is that if it only did one or some subset of those things, that it might get away with it. And I want to make this an easy analyzed crash, so I want it to be caught red-handed, right in the process of doing something bad. So let's go see that in action. So I've got my VM here, and not my fault is showing there. I'm going to press the debug button, and we will see, oh, boom, an instant crash. It's really pretty, isn't it? So let's go analyze that crash together and see what the analysis engine tells us. So the way that I'm going to do that is to open the crash dump in WinDebug, and so actually I should have just stayed there in the VM. So I've saved that crash away from an earlier execution. I'm going to go to Open Crash Dump, select hierarchical here, the dump file that I've saved away. Oh, you know what? I went over that kind of quickly. I went to File, and I went to Open Crash Dump. There's lots of other opens in there that might confuse you. This is the hardest part of crash analysis right there. So make sure you get that step right. So the debugging engine is spitting out some stuff. It tells us bug check analysis, use analyze-b for detailed debugging information. Then it gives us this warning about this particular driver, myfault.sys, which is the driver that I wrote, that it can't find symbols for. And then it tells us, look at that, probably caused by myfault.sys. So it actually successfully figured out, by looking at that crash, that my fault was the problem. Let's do an analyze-b so we can see what went on underneath the hood. And it also will tell us information about that stopcode. Let's scroll up here, and it tells us that this was a driver Urkel not less or equal stopcode. Oh, look at that, the most common one. An attempt was made to access a pageable or completely invalid address at an interrupt request level that is too high. And then it even tells us what those different parameters mean. By the way, the full list of stopcodes are documented in the debugging tools help file. So I'm going to go to the help file, and there's a nice reference in there. The Windows debugging team has done just a fantastic job of making this a go-to place for crash analysis. So I'm going to pick one here, like IRQ will not greater or equal, and let's see what it has for us. It says, bug check 9, Urkel not greater or equal. The Urkel not greater or equal bug check is a value of 9. This bug check appears very infrequently. You can see that this is a tremendous value for you. Actually, I'm not being fair. If you actually click on one of these that's more common, like what we just saw, it does provide you some information. But that information is in the debugging engine itself, and we saw some of that information get spit out. So really, you're never going to even need to open this thing unless you just want to go browsing through the stopcode reference. You maybe print it out, and so you have it handy for you, bedtime reading. So let's take a look at down here, the stack text area. This is the reason why I've explained the concept of stack usage. You're probably like, what? Why is he bothering us with this programming crap? Well, the stack frames of the thread that was executing on the CPU at the time of the crash is the primary resource for the analysis engine for it to be able to make a determination that some driver caused the problem. I'm not really sure that I'm happy with what's going on here, though, because you'll see in a second, as I explain to you what the engine did as it looked at this thing, why I might be uncomfortable. So it started by saying, and you read the stack from bottom to top in terms of what happened first. So the first thing that happened is we entered the kernel from user mode. This is a user mode address. We don't have the user mode stack frames because this is a kernel memory only dump. But the first thing that happened is we entered the kernel, and then we called this function right here, empty device.control file. The analysis engine is looking at the module that each stack frame is in, and it's saying, NT. Who made that? Oh yeah, we did. Oh, we're pretty good, so it's probably not that. NT. Oh, that's Microsoft's code, probably not that. NT. Nope, operating system, not that. NT. Oh, we already figured out it's not that. Ooh, what's this? Ah, third-party driver. Probably that guy. So a little bit of racial profiling going on here. And that's not quite as simple as really it is, but it does use this and weights each frame on the stack for how probable it is that that component caused the crash. It uses a bunch of other heuristics as well, but that's the basics of it. So that was analyzing an easy crash. The problem is that there's lots of crashes that are just simply not easy to analyze. Let me give you an example. Let's say that you have audio driver, and you listen to MP3s and WMAs all day long. So you're running this audio driver all day long. And one day, that driver happens to go down this execution path that it never goes down normally, where it causes data corruption. It overwrites some other driver's buffer, not its own. That other driver happens to be your CD-ROM burning driver. And you burn CDs maybe once every few weeks to save some of those MP3s. And so the system continues running fine. That's the only glitch that the driver has, and you continue to listen to your MP3s, and you might listen for days or days. Your system stays up for, well, it can't stay up for more than a month. But eventually, you decide to burn a CD. And now the CD-ROM driver starts to execute, and bam, it trips right on that corrupted memory and causes a crash. And you go to analyze it, and guess who it points the finger at? CD-ROM.sys. The audio driver might not even be in memory anymore because you've stopped playing music a few hours ago or a few days ago. You could give that crash to a top CPR engineer, and they might look at it and go, hey, there's just no information here. We've got corrupted memory. Can't tell who did it. So that's the case of a victim crashed the system, not the criminal. You can detect these kinds of unanalyzable crashes by either the finger being pointed at somebody you know that probably didn't do it, or you get multiple crashes on this machine where the finger's pointed at different drivers in each crash, or it points the finger at a core Windows component. If you see the analysis engine say NTOS kernel did it, or Win32k.sys did it, or NTFS did it, or another core operating system component, your best bet is to assume that the analysis engine didn't get it right, because it's highly unlikely that those things have bugs in them. I mean, they still might, but highly, highly unlikely. So don't trust it. Basically, consider yourself to have an unanalyzable crash. And your job isn't to go and try to figure out that crash number. Your job is to try to transform that crash from an unanalyzable one into one that you can analyze. And the tool that you can use for that is called the driver verifier. How many people have used the driver verifier before? Just a handful of you. And I think that's a real shame that the word isn't out that this is an awesome crash analysis tool. The driver verifier was introduced in Windows 2000. Its primary goal was to improve the quality of third-party drivers. And in the process, it's also improved the quality of Windows itself. See, the thing is, with drivers execute in this privileged mode where the operating system assumes they know what they're doing. And the problem is that a lot of drivers have bugs in them. So if you believe that a driver might have a bug in it, you can tell the system, using the driver verifier, to watch that driver's execution really closely and to be paranoid about what it's doing and double check its use of I/O blocks, its use of memory, and other operations that it performs. I'm going to switch back to the demo machine and let's take a look at the driver verifier. And you get to it, there's no shortcut. You've got to go to the Run menu and type verifier. And it launches in a nice GUI wizard here. I'm not particularly fond of wizards because when you run a wizard, you don't really know what you're getting. So I like to know exactly what I'm getting, and that's especially the case here. So I'm going to take you down the do-it-yourself path, the, hey, I'm advanced enough to be a code developer path. So select that, press Next. This is where it has you select, it tries to guide you down its default path of picking settings for you. Select individual settings from a full list is the option you want. Press Next, and here you can see the full list of options. I'm going to talk briefly about some of these here. I'm going to save discussion of a couple of them for later. Special pool I'm going to save for later. Pool tracking, not terribly useful for most crash analysis. You use this to have the verifier keep track of the paged and non-paged or kernel heap usage of a particular driver. And that might be useful if you're tracking down a leak in a driver. Forced IRQL checking is worth spending some time on because it's so powerful. See, the thing is, drivers can have a bug where they violate one of those dispatch level rules and get away with it, and the system never knows it. And the vendor can put their driver through all sorts of stress testing, and it never gets caught. But when they distribute it out to a few 100,000 customer machines, or a few million even, it's bound to show up, that bug. And here's a scenario that illustrates this. Let me zoom in again. So you have, let's say you're executing along at passive level. Let me just draw right on the screen here. And the driver, at this point, touches a piece of page memory. So this memory, at that point, has to be physically present in the CPU, in the memory, in the RAM, for that access to succeed. If it wasn't there before, it's brought in at this point in time. Now, a few instructions later, the driver accesses or acquires a synchronization object, the spin lock, which causes the, whoops, oh, my drawing went away. Okay, let me go back. So here's the page memory. And it raises the RQL right here by allocating or acquiring the spin lock to dispatch level. And then it executes a few instructions, and then it goes and references what it just wrote. For the system to detect that this is a violation of the do not touch pageable memory at a higher RQL, that piece of memory has to be sent out from RAM, and it's a lot easier to draw when we're not terminal servered in, so I apologize for, although I'm not a very good screen drawer to begin with. The page of memory would have to be taken out of RAM between point A and point, by the way, I've got a rule, if you've been to my previous sessions, and I've collected some good phones. The ring at the end of the session that had the best ringtone, the phone with the best ringtone, I get that phone. So I'll let that one go because you might not have been aware of the rule. But please turn on your phones, okay? Especially if you have a Motorola Q phone. I really want one of those. So the bug, the only way that this is going to get caught, the only way that this is right here going to generate a page fault is if that page of memory, for some reason, got removed from RAM between those 2 points, and that would cause a page fault here that the system would say, hey, you're violating a rule, I'm going to crash the machine. What the force RQL checking does is causes just that. Anytime a driver raises the RQL up to above passive level, dispatch level or higher, the system goes and marks all of the page memory as not valid. It's still there present physically, but there's no connection between the virtual memory and the RAM. And that means that there will be a page fault, and that driver will be caught right then making the bad move. So force RQL checking is a very powerful option. I/O verification, the next one here, just checks the I/O packets that drivers send to each other and get from the I/O system. Enhanced I/O verification, some more rigorous testing. Deadlock detection detects problems with use of synchronization resources and drivers that might cause hangs. DMA checking, use of I/O system routines for direct memory access devices. Low resource simulation, you're not going to use that for crash analysis because that is used for testing a driver's ability to be out of memory, and you're not really wanting to stress drivers, you're wanting to catch them doing something bad. And then finally, disk integrity checking. That option was introduced in the 5.2 version of the kernel, which is the kernel used on 64-bit XP as well as Server 2003, so you won't see this on 32-bit XP. But this option causes disk blocks when they're written out to disk to be checksummed, and then checksummed again on the way back, and if there's a discrepancy between what the system saw on the way out from what came back, the system assumes that there's disk corruption going on and crashes the machine. So the crash analysis recipe is going to have you select all of these options except for low resource simulation. The next page is going to ask you which drivers you want to verify. And it's going to, again, give you some options here. And this is where the crash dump analysis recipe comes into play. Let me just show you this, and then we'll switch back to the slide that explains that. Automatically unselect unsigned drivers. That's going to be one possibility for the crash analysis recipe. This one you're never going to use. This one you're never going to use. So this is the other one that you might use. And if you select that one, you get taken to a page that lists all the drivers present on the machine and lets you check them individually. So let's go back to the crash analysis recipe now. Which is shown right here. First step, if you're getting crashes you can analyze. Point the verifier at any drivers that you suspect might be causing the problem. Recently updated, known to have problems. If you still get unanalyzable crashes, so you're still getting those crashes pointing the finger at stuff you don't trust, then move on to step 2. Select all the settings you did for step 1, but go down that all unsigned drivers path that you saw the verifier give you the option for. If you're still getting unanalyzable crashes, last resort, go after all the drivers, but do them in groups of 10 to 20 at a time. The reason why you don't just want to say all is because you're going to be doing two things. Crippling the performance of the machine, and if you want to see what it's like, go ahead and try it, see how long it takes your system to boot with this on. And 2, you're going to be crippling the effectiveness of the verifier. One of the options, the special pool option, becomes basically useless if you select more than a few drivers. and you'll understand that in a minute. And then last option, run the Windows memory diagnostic. Or you can do that at any point, of course, to see if really it's a memory issue. I'll talk about that shortly. So I'm going to show you two examples that transform an unanalyzable crash into an analyzable one, starting with the buffer overflow. So buffer overflow is a very common bug for Windows programmers that program in C or C++. Very easy to accidentally go off the end of an array, one entry too far. And if you do that in a driver, you go past the end of your driver buffer and you end up either in the pool tracking data structures, the heap manager structures, or another driver's buffer, which is the case that I described in that scenario where you've got your CD-ROM player and your audio driver. There can be a really long delay between corruption and detection. Let's go see just how long the delay can be. So I've got the VM here ready to go. I'm going to select buffer overrun. Every time I press the debug button here, I've corrupted memory. Oops, I don't know if I can get the mouse to move over there. Here we go. One. Oh, that time it happened right away. Nope, actually, I had the wrong VM resumed. Apologize for that. Let's do that again. So buffer overflow. And okay, here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. When you get tired of doing this, or when I get tired of doing this, which I'm getting tired right now, I just run IE. It'll take a second. The VM is still restoring, so IE is going to take a second to start up. Here we go. And you know what? When IE doesn't do the job, then I fall back on trustworthy old Windows Messenger. And there we go. So that illustrates just how long of a delay there can be between this kind of bug and the problem that caused it. The problem it causes, actually. So how do you debug these things? Well, if you turn on the verifier and you point it at that driver that just caused the problem, my fault, and you do that using the crash analysis recipe, you're turning on special pool. And that means the driver is being verified. When they allocate memory, they don't allocate it from normal pool. They allocate it from a special region of memory, hence the name special pool. This special region is like a checkerboard. Every other page is invalid memory. And the driver's buffer is aligned against the top of one of these pages. By the way, this whole special pool concept's been taken to user mode, too, with the app verifier. The driver now, when it goes off the end of its buffer, boom, right here, invalid page, page fault, system's going to detect it right away, and it's going to crash. And this special pool, like I said, is the reason why you only want to verify a subset of drivers at a time. Special pool is a very limited resource, and if you went and turned the verifier on all drivers, once special pools run out, drivers get their allocation satisfied from normal pool, which doesn't have this kind of error checking in it. So you might miss the problem altogether if you're verifying the driver. If the driver that is causing the problem has this allocation not serviced from special pool. By the way, this is one of the options, one of the few options you can enable without rebooting the machine. So let's go back and do that same crash, except this time with the verifier on. So buffer overflow, and this looks the same way that I just showed you. I press debug, and bam, crash. Now, what I didn't fail to show you before was the crash analysis of that first crash, and let's compare that with the crash analysis of that second crash, the first one being the one that had the long delay. And by the way, I've saved these crash dumps off from earlier versions of that crash. So here's buffer overflow and the crash analysis engine. Let's go ahead and do an analyze-v, but if you quick reader, you can see it's pointing the finger at a driver already. For some reason, I can't get the, here we go, analyze-v. And if you scroll up, the stop code is driver corrupted pool, which makes sense given the circumstances. And if you look down at the stack, here you can see the weighting at play, because there are three modules, three components in this stack trace. There's the HAL, the hardware abstraction layer, there's NT, and then there's this RAS ACD driver. All of these are components of the OS. But the weighting says that RAS-ACD is more likely than either HAL or the NTOS kernel to have caused the problem, and hence, it pointed the finger at RAS-ACD. Now, we know for a fact that that's not the driver that caused this problem. This is an unanalyzable crash. Every time you run it, you'll get a different kind of analysis. So let's go and open the crash from the special pool run, buffer overflow with special pool. And this crash is going to look very familiar. It's going to look a lot like our first one, analyze-v. And so if we scroll up here, driver page fault beyond end of allocation. So it detected that the driver had overrun its buffer, and if you scroll down, it points the finger at my fault, and the stack looks exactly like the stack that we saw for that first crash, where my fault was caught red-handed. So a case of turning a unanalyzable crash into one that's analyzable. By the way, we started a few minutes late, so I am going to be going a few minutes over noon. And I apologize if that causes people inconvenience. The next type of unanalyzable crash we'll take a look at is code overwrite. And a code overwrite is caused when a driver has a wild pointer because of a bug, and it overwrites not somebody else's data, but somebody else's code. What's going to happen here is the same thing. Another driver whose code that belongs to, or the kernel, comes and trips on it and causes an illegal operation, and the system points the finger at it. There's a feature of Windows called system code write protection that is aimed at detecting that kind of bug right when it happens. But the problem with that feature is that for performance reasons, the kernel turns it off if on a Windows 2000 system you have more than 127 meg of memory, or on a Windows XP or Server 2003 system you have more than 255. In other words, it's never on. So how do you get it on? You turn on the driver verifier and you point at any driver at all, or you can go and manually set it in the registry. And so let's go take a quick look at the code overwrite case in not my fault. And it's right here, and we'll get a crash instantly. But when we go look at that crash dump, it's actually going to be pointing the finger at not the guy that caused it, but at whoever stumbled on it. So let's go and open crash dump and go for a code overwrite. And there's a different stop code number that we saw there. It's K-mode exception not handled. The mouse is going crazy. K-mode exception not handled. Another one of those very common ones. And it actually says, oh, by the way, this is very common, like you cared. Usually exception address pinpoints the driver or function that caused the problem. Let's scroll down and look at the stack. And, well, there's no third-party component on that stack. It's win32k.sys, which is the Windows subsystem driver, and NTOS kernel. And if we look at who it pointed the finger at up here, it's, well, memory corruption. Memory corruption. So it didn't even bother pointing the finger at it itself. It just says, hey, I know that memory's been corrupted somehow. If you did that same crash now with the driver verifier on, you're going to get an instant crash again, but this time when you open the crash dump, so it's code overwrite with write protection on. This is going to be old news at this point, because when we analyze it, analyze-v, if we scroll up and look at the stop code description, it says attempted write to read-only memory. That's because the code that was overwritten has been marked as read-only by system code write protection. If we go down and look at the stack, well, looks just like the one we saw with the buffer overflow and verifier. It looks like just like the one we saw with that first easy to analyze crash. And there's myfault.sys sitting right in the driver's seat for this crash. So that's examples of using the verifier to transform unanalyzable crashes into ones that you can analyze. But there's going to be cases where you go through the whole recipe, and, whoops, I went a little too far there. Let me go back. This is where the slide transitions kind of get in your way. And I don't remember offhand which slide that was, so we're getting close. Here we go. So the crash analysis recipe doesn't give you an answer that you can rely on. So the tool that I mentioned is the Windows Memory Diagnostic. Worth running that at any point in the crash analysis process to see if maybe it's a memory problem, especially if you're getting memory corruption or crashes all over the place. It's a free download from the OCA website. Here's the URL. But if you go search for Windows Memory Diagnostic on Microsoft.com, you'll find it. It installs to a CD-ROM or boot floppy that you boot the system from, and when it launches, it just runs this test continuously of testing banks of memory with different kinds of memory checking algorithms, and will flag down there in that area any errors it encounters, including what bank of memory it might have encountered that error with. So you can figure out which DIMM caused that problem and pull it and replace it. Run it through at least one pass, which might take several minutes. But let's assume that you've done that now, and you're still getting unanalyzable crashes. Sometimes you need to go in and just poke around, look for clues. And there's no guidelines here. It's a matter of you getting some experience or trying some different kernel debugger commands, reading through the documentation, and just poking around to see if maybe there's something to latch onto. Because at this point, you're desperate, right? It's between, if you're getting crashes and you're getting to this point in the analysis recipe, it's reinstall or, I guess, deal with the crashes. So one of the commands is lmkv to list the drivers that are running on the machine. We'll see that in a second. Bang VM, useful for troubleshooting those memory leaks that are causing crashes. So this will show you if non-page pool or page pool has run out. And that might be the cause of the crash, in which case you'd have to go do a leak analysis using the verifier. Look at what the current thread is doing with the bang thread command. It may or may not be related to the crash, but it might help you with a clue. Especially on server systems, do this. Bang process 00 to look at what processes are running on the machine. On a server, you need to understand, especially if it's mission critical, the purpose of every single process on that machine. For that matter, you should understand the purpose of every driver on that machine and make sure that you're up to date on all of them. Additional commands you can get through with the bang help. Of course, the help file is good too. This next example is a stack trash, which is a crash you can generate without my fault, where it will blow its own stack of its thread. The stack being the primary resource for the stack analysis, the analysis engine is not going to be able to pinpoint the cause of the crash. In fact, even if you turn on the verifier on with all the settings and point it at my fault, you're still not going to get a crash that you can analyze. Let's go take a look at that crash. Oops, I think I didn't get out of live meeting the right way. So here we go. I've saved off that crash dump from the stack trash. Let's open it up. And let's do a bang analyze -v. And it's a K-mode exception not handled. That flew by really quickly. The stack trace doesn't tell us anything. MT is the only module on that stack. And so the system really had no choice but to say, well, NTOS kernel probably called it, which is what would show up in the probably caused by. I'm going to do a bang thread to look at what the current thread at the time of the crash is doing. And one of the things that Windows keeps track of is the I/O operations that a thread has outstanding in this I/O request packet list. If I do a bang ERP command to look at that I/O request packet, it'll tell us what driver that I/O is aimed at. And whoops, I did something funny there. Oh. Control V is what I'm trying to hit, and that didn't work. Control C, and then Control V. And what it tells us is that I/O request packet is aimed at this driver right here, my fault. So even though the stack is blown, we have a clue, and this would be, at this point you're just grasping for straws. Go take a look, make sure you know what that driver is doing, and you've got the most recent version. So how about crashes that don't generate dumps? We're back to that scenario where you've configured the system to generate a crash dump, but you're not getting it. There's two options here. One is to boot the machine in debugging mode. You can do that with the F8 key during the boot process. Do not do it that way. Warning, warning. Do not do it that way. What that does is causes the debugging and code on the system you're booting to assume that you're going to communicate with that system over a serial port, a serial cable, at the lowest baud rate supported by Windows, which is 19200. So if you're going to try to troubleshoot a crash over that kind of connection, you might as well connect the debugger to it and then take the day off, come back the next morning. So what you want to do is modify the boot.ini with switches that cause it to use a higher baud rate or an alternate connection mechanism like IEEE 1394 or in Vista USB 2.0. In either case, the kernel debugger on what's called the target, the machine you're troubleshooting, is loaded. But it does not affect performance. That is, not performance until the system crashes. Because even if you've got it set to auto reboot, if you've booted in debugging mode, it will sit there waiting forever for you to walk up with another computer, connect to it over that communications port you specified, and then debug it. So this is when you attach the kernel debugger and analyze it. In WinDebug, you use the file kernel debug option. Let's go back and quickly take a look at that. That option is here, File, I need to stop debugging, and then go to File, Kernel Debug, and you can see the different options, COM, 1394, and USB. You connect to the machine, and when you've connected, you're basically looking at a crash dump that hasn't been saved to disk yet. And so everything I've told you about analyzing a crash applies. You do your bang analyze -v. You can also save the dump for offline analysis. Use .dump to save a mini dump off, or if you want the full contents of memory, unfortunately there's no kernel dump option here, type .dump f, and that reads the contents of physical memory over the connection and saves it in a target file on the local machine. Note, don't do that over serial cable. Now, hung systems, another type of crash that doesn't generate a dump. Two types of hangs that I've experienced: instant lockup, and then the slow grinding to a halt, where you do something, that doesn't finish, you do something else to try to look at what's going on, that doesn't finish, you try to launch Task Manager, it never shows up, and then the system totally locks up. To analyze a hung system, you need to take some steps ahead of time. You need to, and you've got two options here: booting the machine in debugging mode, or configuring it so you can crash the machine manually. So I've already described how you boot the machine in debugging mode. Let's talk about the other option, initiating a manual crash. And there's two options here: crashing from the keyboard, which you configure this registry value here. For the PS2 keyboard driver, the parameters key, crash on control scroll, you have to create that value, set it to 1. This is documented in the help file. And that means that when the system sees this special keystroke sequence, which is right control held down with scroll lock twice, then the keyboard's interrupt service routine will crash the machine. Call kdebug check EX. The second option is to configure a dump switch, or use the dump switch. Some servers come with an NMI button, non-maskable interrupt. To cause this Windows to crash when it sees an NMI signal, you go configure this registry value right here. You can also make your own dump switch in case if you've got a system that doesn't have one. And you visit this website, and it tells you for about $8 how you can go to Radio Shack and buy a button, connect a wire to it, and then connect it to the NMI pin on your motherboard. And if you've never done this, I highly recommend it. It's very gratifying. So now that you've got a crash or you're broken into a system that's hung, your next step is to analyze what's going on. And this is the hard part. Well, actually, let me back up a second. If you've booted the machine in debugging mode and it's hung, you walk up with the second machine, you connect it with the kernel debugger using that kernel debug option. At that point, you've got to hit the break button or type Control-C, and that will send a signal to the kernel debugger on that target machine telling it that you want to break in. In some cases, you're not going to be able to break into a hung system. And those situations occur when the RQL of the hung system is above the keyboard's driver, and you've configured it for keyboard crashing. Or the system is so hosed that even the NMI interrupt handler is not going to be responding. So what you do at this point, you analyze it the same way we've been analyzing it. Use bang thread to see what's running. Use bang locks to see if there's any possible deadlocks, and that's documented in the help file. Use bang RQL to see what the previous RQL was. If you can't figure it out but want to save the dump for later analysis because you want to reboot the machine quickly to get it back into service, use .crash to force the system to crash itself. And that will cause the dump to go to the target machine's crash file. Or you can, again, use the .dump command to save the crash image to your local machine for analysis. So let's go generate a hung system using not my fault. So I'm back in the, I didn't mean to resume that one. Let me resume this one. This is a version of the VM that has that crash on control scroll lock key. Oh, you know what? Was this going to work? Yeah. So I'm going to select hang. This should work over a terminal server connection. And I'm going to say debug, and that machine is totally frozen now. can do whatever I want to, but I'm going to hit right control and then find the scroll out key, which I don't know if I've got a this keyboard has a funny indicator on that key, so I'm not sure what the button is that I need to also press for it. Maybe shift. Okay, this is not going to work. But what would have happened, I would have hit control, scroll lock, and the system would have blue screen instantly. And if you go look at that dump that would be generated by that, which I've saved away from a previous execution, thank goodness, you're going to see a crash that looks like this. First of all, the analysis engine is going to tell you that the keyboard driver caused the problem because it technically did. It called debug check-ex. If you do a bang analyze -v, you're going to see the stack of the thread at the time of the crash. And there it is. So my fault was running, and then it was interrupted by that keyboard key press for that last control, that last scroll lock. And then the keyboard driver took over, and it saw that this was the second scroll lock in that sequence and called debug check-ex right there at the top. So what was happening? My fault was running. Big clue that that might be the problem. And I've got a couple of crash scenarios from a real system at home that I experienced. Let me set this up. So I had this system that was periodically hanging. Wanted to troubleshoot it. It was a family computer, actually. So I went in and I configured it to crash on control scroll. I rebooted the machine, and lo and behold, it crashed at the reboot. So I went in and I opened the crash dump file for it to look at what was causing this new crash. And I'd forgotten to flip the thing to use kernel dumps, so I've got the mini dump from that crash. And this is what it looks like. And here we go. Analyze -v. Well, actually, I don't even need to do that. You can see right there, it figured out who it was probably caused by. If you look at the analyze -v, the reason it picked on that, driver equal not less or equal, was, well, there it is right on the stack, being called at dispatch level, because this function executes at dispatch level. That driver, I did a lookup on. So I did lmkv on it. You've got to do this magic syntax, which is documented. And I saw the timestamp that that driver had on it. Very, very old. I went to the vendor's website. I'm not going to embarrass the vendor here, but let's just say that they're known for audio devices. And figured out that they had a much newer version of this driver, downloaded it, installed it. Installed it, rebooted the machine, and to my great joy, it hung after the reboot. So I had the opportunity at that point to do the crash on control scroll to see what was causing the hangs. And I've got the kernel dump from that, and this is what I saw. Well, first of all, it's going to tell us manual crash, but then I did a bang thread. And I saw this. This driver, WPN111, which happens to be a wireless network adapter driver, calling ndis acquire spinlock. And then it got interrupted by the crash at that point. So it was trying to acquire some spinlock, never being able to acquire it. Note that there's a 0 down here, and the kernel debugger works on multiprocessor machines, and it lets you look at what's going on in each CPU. It tells you which CPU you've got to focus on right there. This is a two-way system, and I'm on CPU 0. Ooh, that was a nice ring. So I'm on CPU 0. Let me switch to CPU 1, which you're going to want to do if you get a hang. Look at every CPU and do the same bang thread. And the stack looks similar. It's not quite as deep, but it's that same driver trying to acquire spinlock. This driver, I did the LMKV, figured out it was an old version, went to the vendor's website, downloaded the new version. That system has been problem-free since this fantastic afternoon, very exciting afternoon of crash and hang analysis. So one last thing, analyzing a SIX system, if they're, here we go, went a little too far. Analyzing a SIX system, sometimes the system is still responsive, but you know something's wrong with it. You can get a dump of that system to analyze offline, and the reason I'm telling you this is Microsoft PSS. Several people there have told me that they use this to troubleshoot customer systems to get dumps of them that they can go analyze without crashing the server until they figured out what the fix is. And you use the tool called LiveKD, which is a free download from sysinternals, will trick the kernel debugger into thinking it's looking at a crash dump when it's looking at a live system. You can do .dump in there to snapshot that system's memory state to disk and then take it offline to go analyze. And then one final thing, I'm going to switch over to my real laptop here. Oh, see? There we go, wake it up. And should leave you with one last summary slide. I dismiss the reminders and I get the control of my desktop back. And I apologize to the web viewers that you can't see this summary slide. And that is right here. And uh-oh. Well, I guess that's fitting, isn't it? The end of a crash talk to have a crash. Actually, that's not a real crash. That's the Blue Screen of Death screensaver, which is a free download from sysinternals that mimics a real-looking crash. But if you wait long enough, it also simulates a real reboot. And I want to just, if you want to, that's when it looks like it's going to succeed in booting. We're going to get another crash in a second. But I want to share with you a little story. This screensaver is so authentic looking, it's fooled kernel developers at Microsoft. It's fooled Dave Solomon, and it's even fooled me. There was one day we were teaching a seminar together, different rooms, and I took a break, and he went into my room, and the screensaver was running like this, and he comes running down the hall. Mark, get back in there. Your system's crashing and rebooting. Dave, chill. It's just a screensaver. Oh. But it's also been used on Brian Valentine himself. See, he was the head of Exchange 5.5 before he moved to Windows. And he's very involved with the development process. As Exchange 5.5 neared its release date, he would go to the test lab every morning when he came to work. And back in those days, you had individual monitors connected to the computers. He'd wake them all up, go down to the end of the room, and turn around to see if there was any problems. The test team started to see this pattern develop. So they decided to play a little prank on him. On the night of the RTM release test, they load the screensaver on all the machines. He comes in the morning. He wakes them all up, turns around, and sees nothing but blue. And if you know anything about Brian Valentine, you know that his reaction was a little bit colorful. They anticipated a colorful reaction, and they had mounted a video camera in the corner of the room. And maybe that explains why he's a little bit annoyed with blue screens. But that video, actually, I've never even seen. It's more closely guarded than the Windows source code. And I want to leave you with one last tip on how to get maximal usage out of the Blue Screen to Death screensaver, and that is this psexec command, psexec being a free tool from sysinternals, that you can use to launch it on somebody else's machine. And so that brings us to the conclusion. There's more information. Everything I've talked about is in Chapter 10 of the Windows Internals book. So all of those crash examples are in there, complete with a full discussion of what you saw. The knowledge base, other books are available on that URL. Please fill out your evals, and I thank you very much for coming. Hope you're crash-free in the future.
Well, ladies and gentlemen, that concludes this afternoon's TechNet webcast. I'd like to thank you all for joining us. We have put a survey up on the screen for those of you joining us via live meeting. If you could take a few moments and fill out the survey, let us know what you thought of today's presentation. We greatly appreciate the feedback that you have to offer us. Well, and again, I'd like to thank Mark for presenting today, and thank you to our team that was helping out in the background to answer questions. There's still a few questions in queue, and they will get to those. Again, if you could fill out the survey, we greatly appreciate it. Remember, when you fill out a survey at any Microsoft webcast through the month of June, you'll automatically be entered to win a free 40 GB Creative Zen Ultra MP3 player. This concludes this webcast. Thanks for joining us. Have a great day.